Hi everyone. This molecule is an example of something that might be used in organic electronics. It's got an extended conjugated system across the whole thing, so it's really good at absorbing light, for example. We would call this system a chromophore, or maybe even a dye, because it will likely absorb quite a lot in the visible part of the spectrum. So these types of molecules can potentially be used in organic solar cells for harvesting light, or maybe in OLEDs for doing the exact reverse if they're part of an electric circuit, as in if they're stimulated, they'll give out light. Now this is known as a push-pull chromophore because it has a donor end at the right, by which we can see it's got an electron-rich ring, and it has an acceptor on the left-hand side. This is electron poor. So the reason why molecules like this are particularly effective is that in this push-pull system, the molecular orbitals across the whole molecule will be very polarized. More of the unoccupied orbitals polarized to the left, and more of the occupied ones polarized towards the right. This means that when this molecule, say when it's being a solar cell, absorbs light and excites an electron, we can get fast transport of the electron across the molecule. The charge distribution changes quite a lot across the molecule, and then we can use this molecule as part of a semiconductor device to generate electricity in that case. But today I want to focus on how to make a molecule like this, and also because we might need to engineer a device by making this molecule, I want to take a modular approach. I want to build this molecule like it's Lego so that I can make a library of similar molecules to see which one will work best in my electronic device. Now, we might have a reasonably good idea about what the molecular orbitals will look like for this thing from calculations, but in building organic electronic devices, we also need to be able to make sure that we can build the device in the first place. Otherwise, rather than making an intended semiconductor, we might get something that, say, crystallizes in a way that just means you've made a really expensive resistor. Now that brings me to one point down here, that these alkyl groups down here, so hexyl groups, they're here for solubility. If we just had loads of aromatic systems strung together, you'd have a hard job keeping things in solution and being able to do any sort of organic chemistry on them. It's also important to keep these molecules in solution, so when you make your electronic device, you can grow crystals into careful shapes. That's an important feature for getting the desirable semiconducting properties of the material when you're making a device. Okay, other features we've got, well, we've sort of got multiple heterocycles. We've got two triazoles acting as spacers. This core in the middle is called a fluorine. An unfortunate naming there, I guess, but it's spelled like this with an E rather than an I. On the left-hand side, we have a pyrimidine. And on the right-hand side, well, we just have a substituted benzene. This is an aniline derivative. So a modular approach will allow me to build up this molecule into bits. So ideally, I'd like to build each of these heterocycles in turn and stitch them together. So then if I want to change one of them, I can do that easily without having to redesign a whole synthesis. Going forwards, I'm just going to abbreviate those alkyl groups just to hexyl. So that's C6H13. So a key part to this modular approach will be to exploit these triazoles. In fact, that aromatic ring is incredibly useful for just sticking molecules together like Lego. And that's because we can use a cycloaddition. And in fact, this chemistry is quite widespread now, often used in biological contexts, and is usually referred to nowadays as click chemistry because we can just click the molecules together. So what components do we need? We need to make these three molecules. We'll need the pyrimidine with an azide functional group. The fluorine core needs to be flanked with alkynes, while I need the aniline derivative to also be bearing an azide. Now, just having a look at that reaction itself, the general idea, if we have an azide and an alkyne and we heat them up, we can get a pericyclic 4+2 cycloaddition to go straight to the aromatic triazole. Job done. One step, very clean, no byproducts. But there is a slight issue here. We probably want an R group on our alkyne. There's two different isomers that we could form here. If it arranges itself with the R group like this, I'll get this product with the triazole. But the alkyne, of course, can arrange itself in the other direction, and we'll get a different regioisomer of product. So specifically this one with the R group in a different position. Now, this is a pain if we want to do selective chemistry and form pure products. It might be tricky to separate those, for example, and we'd certainly be sacrificing yield. Now, a key breakthrough in this area was to add copper, and that helps organize the starting materials. So that this time, well, first we probably get some sort of interaction with the copper with the pi system of the alkyne. That's a pretty well-observed phenomenon in chemistry. That makes the proton on the end a bit more acidic. So it's possible that we formally make the cuprate like this. In both cases, that R group is a bit of a steric block. But importantly, the copper can coordinate the azide so that we get an intramolecular type delivery. Now, on the right-hand side, we can maybe see how that's done a bit more clearly. We have a formal negative charge on our azide. So we can see that there could be a clear nitrogen to copper interaction. So now when the cycloaddition proceeds, we'll end up with an isomer that looks like this one here, where the R groups are further apart from each other. You can make a similar argument just drawing it on the first one. You'd need to do kinetic studies to prove which way was which. But here the argument would just be keeping the sterics of the R's apart. We can get our cycloaddition happening again. Both of these mechanisms show that we get a preference for this isomer, which is often called the 1,4 isomer. I've just drawn the numbering conventions for triazoles there. And now we have a reliable way for making one isomer of a triazole. And luckily, that's the one we needed in our retrosynthesis. So I need to be quite clear that we need to use this click chemistry with a copper-1 catalyst. Now, this is becoming a bit of a mouthful. This is normally referred to by this initialism, CuAAC. That's the copper-assisted azide alkyne cycloaddition. This reaction gets a lot of utility all over organic chemistry, particularly in chemical biology, because you can get this reaction to work in aqueous conditions and also in biological type conditions without messing anything else up. So for example, it's quite a good way of attaching fluorescent probes to things, to say drug candidates, so you can probe the biological system. So that's our key strategy. Now there's one issue we have to identify first, is that our middle unit is symmetrical, has two alkynes, which are chemically identical. So we're going to need to differentiate them if we want to make sure that one side gets the electron deficient heterocycle and the other side gets the electron rich one. So actually what I need to do is make sure my fluorine has some protecting groups on it, which I can just remove in turn and then mask each alkyne when I need it. Standard ways of protecting the alkynes would be to use silicon. So I'm going to use two different types of silyl protecting group, one small one, trimethylsilyl, and a bulkier one on the other side with a silicon with 3 isopropyl groups on it. Now, the isopropyl one is often referred to as a TIPS group, and the trimethyl one is normally called TMS. So my plan is, if I can make this molecule, I could do a selective deprotection, do one click reaction on one side, and then deprotect the other alkyne and do the second click reaction on the other side. This is the Lego type approach, which will help me build up a library if I wanted to vary the other heterocycles. Okay, and to make this, well, I need to find a way of getting those alkynes onto that central core, and I could use Sonneger-Shearer couplings to do this. So these are palladium catalyzed cross-coupling reactions. I need to worry about the symmetry again and that I get differentiation between the two sides. But what I disconnect back to is the fluorine core here. So I'm going to need two different leaving groups here, X and Y, that can participate in oxidative addition. Unfortunately, if we think about halides, we have that available to us. If we make one of them the iodide and one of them the bromide, the Sonneger-Shearer coupling will be way faster for the species with the iodide. So we'll be able to do it at low temperature or something, because palladium 0 can oxidatively insert into that carbon-iodine bond much more quickly than it can into the carbon-bromine one. So some final disconnections on here, which I'll use a new slide to explain, are that we're going to need to get those two halogenations in there, and I can also take off these hexyl groups to disconnect us back to just fluorine, which is readily available. But before we get there, let's have a plan of how we make the other heterocycle components. We need to make the pyrimidine and the aniline as well. So just starting with the pyrimidine, well, there's not too much to do here. We have a reactive functional group in that azide. A sensible disconnection would be across here to allow us to do some substitution chemistry to take me back to the aryl chloride. Now, with those nitrogens in the positions that we are, it should be quite easy to go backwards just using sodium azide as a nucleophile. And that's just because we can just do an SNAR reaction, the N3- coming in, kicking up and kicking back out like this. Now, how do we make aryl chlorides? Well, for this heterocycle, we can make it from the pyrimidone. This can exist as tautomers, one with a hydroxyl group off the end, but it's more likely to exist with the hydrogen in this position. We can just use phosphoryl trichloride to get that reaction to work, so POCl3, POCl3, just some standard heterocyclic chemistry here. The phosphoryl trichloride will react with the oxygen, and the oxygen will be activated as a leaving group, and the chloride anion can come in and do SNAR. And the final disconnection is just a condensation. A classic way of making a pyrimidone would be to start with the diketone here, which is readily available, and do a condensation reaction with urea, which of course is also readily available. You can kind of see how this works. We could condense to form an imine or an enamine with those nitrogens. So we do it on one side first, then it can happen on the other side intramolecularly, and we can tautomerize to aromaticity. So quite straightforward for this one. But the molecule we're trying to make actually has some interesting chemistry. The product we're trying to make here actually doesn't quite exist as that structure in solution. It's in equilibrium with something else. In fact, the azide form here isn't its major structure in solution. I'll just draw the azide out. The molecule readily does an electrocyclization and exists mainly as this tetrazole form. Now we can just do a quick electron count to justify why that might be the case. Well, we can see that there's 2 electrons here in each of these double bonds and 2 electrons being donated by that nitrogen. So this is actually a 10 pi aromatic system. So that's why it's more stable. But importantly, it's unreactive. It looks a bit scary to me with all of those nitrogens in there. But this is all right if we use this temporarily, because we can just wait for it to convert to the azide form. The azide can do the copper-assisted cycloaddition, and then by Le Chatelier's principle, we'll just keep making more of the azide as and when we need it, because these two are in equilibrium. Now, this form's quite interesting to have a think about the retrosynthesis on, because we might want to do something a bit different, because it shows us that there's another path to make this molecule. What I'm going to do is focus on the tetrazole component here, and I can see that if I had a substituted tetrazole, I could just do the same condensation that I had above. In fact, I could do it in a slightly cleaner way in practice and minimize my byproducts, in particular lots of phosphorus waste, I guess. So it'll take me back to the same diketone that is readily available. What I need is this tetrazole with the amine substituent, because, well, I can see that I can condense the amine onto there to form the imine or the enamine again. And then I can just do a condensation of this other nitrogen to form the bigger heterocyclic ring later. But it's quite easy to make this. And that's because I can disconnect it quite easily back to this readily available starting material, which is called cyanamide. And I can react that with the azide anion and do a standard cycloaddition. So I'm just going to source this from sodium azide as the salt. So there's 2 alternative pathways we could go here. This bottom pathway is maybe more exciting, but I'm a bit iffy about this molecule in the middle. I would worry that that would be pretty explosive given its nitrogen content if we weren't pretty careful. Okay, so this will be the final component we need, and we can just do some aromatic chemistry to make this. The azide is the reactive functional group, so we should disconnect that first. And how do we make azides? Well, they're quite easily made from the hydrazine, and that's because to go backwards, we can just use nitrous acid as a diazotation type reaction. I'll just come back to that one in a second, because in fact, we're going to need to use the same reaction to make the hydrazine in the first place. We can make the hydrazine by reduction of the diazonium salt. There's lots of different reducing agents we could use here. We could use this dithionite, or traditionally we could probably use like tin chloride. In any case, this is a reducing agent, with water being the source of hydrogens there, of course. Now a diazo compound, well, we make it by diazotation, so as before, make that from the amine, and I can just use nitrous acid. So just to be clear what the mechanism for those types of steps are. If we have an amine, nitrous acid decomposes into the nitrosyl cation, which is a powerful electrophile, will generate species along this lines, which can then transfer protons to form species like this, and do the same again to make a leaving group, and generate the diazonium salt. It's a pretty old school reaction, but pretty easy to do on simple substrates. So back to the retrosynthesis, could make the amine from the nitro compound just by another reduction. Use your favorite things here. We could use tin HCl, for example. And then we're in a good place because we have an electron donating group and we want a substituent in the para position. So we should just be able to nitrate that using nitric acid and sulfuric acid. But we'd actually be wrong in this. This will not work using those conditions. Cooking up that amine in a load of really strong acid, we'll just protonate it. And now we have an electron withdrawing group on here, which if it does anything will direct to the meta position, but it's also a cation. So it'll have very low reactivity with the nitronium ion that we want it to react with. 2 positively charged molecules to react with each other. There'll be a very high activation energy for that reaction, to the point where our yield is likely to be pretty low. And even if we do get a reaction, it'll make the wrong isomer. So the standard chemistry here has failed on even something that looks reasonably straightforward. So how can we fix this? Well, let's have a think of some other strategies. Just to address one issue first, perhaps I could install that azide via some sort of Ullmann-like coupling, by which I mean we could disconnect it back to the iodide, and then maybe react it back with a copper salt. Copper iodide would probably be a good idea, and sodium azide, and then hope that we get transfer of the azide ion. Now, we can probably optimize some conditions along this sort of lines, and there is research out there for doing chemistry like this, but unfortunately it doesn't really address the problem. We would need the aryl iodide, but that just generates us some different types of pain. Again, it looks like we should just be able to halogenate on here, and we specifically need the iodide for this type of chemistry. It looks like we should just be able to do a parahalogenation here, but we run into another problem. This is not the same as brominating or chlorinating a benzene ring. The classical way of doing this would just be to use I2. With chlorine and bromine, we'd need to add a Lewis acid at this point to activate the halogen to reaction, but there aren't many good Lewis acids that are good for coordinating to I2, and there certainly aren't any that are particularly cheap. Lots of Lewis acids will just have redox chemistry with I2 and not do the thing that we want it to. So unfortunately, the reaction conditions require a strong oxidizing agent to be in there. That's often requiring nitric acid to be present as well. So we end up with the same problem of the acid, that we'd protonate the aniline. Just as a side note, the reason why that works is that it can oxidize the iodine to a more reactive iodine-1 species, which would now be a better electrophile. Interestingly, these conditions are doubly useful because the iodide ions themselves do redox chemistry in the presence of a strong acid and heat, and they can reform the I2 molecule that we need. So actually, we would only need half as much I2 as we might be expecting. We're not going to be throwing any of that element away as anions in that reaction. Now, I'm not going to deny that there might be another way of doing this. I was just sticking to some classical chemistry here. We might be able to do this iodination with NIS, N-iodosuccinimide, as a more reactive iodine source. But either way, we're encountering issues. I think there is a way forward just using very traditional textbook chemistry. If we focus in on this intermediate that I've just circled in yellow, and we just reverse the perspective here. What I'm going to do is use the other nitrogen to be the directing group, and I'm going to use something that's very reliable instead. And what I'm going to do is just do a functional group interconversion to the amide, which is a very well-behaved paradirecting group. No longer has a basic lone pair on this nitrogen because it's busy delocalized with the carbonyl. And I know we can quite easily go backwards. So my key disconnection, well, I'm going to try and form this bond here. So I need to add a nitrogen to the ring. So I probably want to go via a nitro group. As we saw before, one thing we could do is use the nitro group to go to the amine, because that itself can be obtained by reduction of the nitro compound. Then we've just got this acetanilide, which can be made from aniline. So just checking the sequence, we should be able to acylate here, acetyl chloride and pyridine. Next step, well, the nitration looks like it should be okay now, just using standard conditions. The reduction, tin HCl would be standard conditions for that. That all looks good. And then we just need to methylate the amine. Well, I think we can probably just do this with methyl iodide. We do have a nitrogen lone pair there that can be a nucleophile. So we can methylate once, the lone pair will still be present. We can methylate twice, but I think it's quite unlikely to methylate 3 times. Well, it will certainly be a less favorable product than just adding 2, because we would lose conjugation of the lone pair with the benzene ring. Okay, now we've got all our bits and pieces. Let's put them together in a modular forward synthesis. So we said we'd start with fluorine. Now this is a pretty cheap starting material. As I'm recording this video, you can buy 1 kilogram of it for $360, that's US dollars, from standard chemical suppliers. For context, that's actually 6 whole moles. So that's really quite a lot there. The key feature of the fluorine is that these protons here are acidic. If we imagine deprotonating one of them to get the anion here, it would be fully delocalized over the rings. In fact, it would form a 14 pi aromatic system here. So this is pretty acidic for a hydrocarbon. In fact, the pKa of those protons is around about 20. So that means to get my hexyl groups on, I could just do some standard SN2 chemistry using hexyl bromide or hexyl chloride and just making sure I've got a base in there. We could use something like terbutoxide to minimize any elimination risks. Once we've got one of the hexyl groups on, there'll still be another acidic proton, so it can deprotonate again and add the second hexyl group, and that will give me this product. Next step, I'm going to do a monobromination, just using some standard aromatic chemistry using bromine and iron bromide. But it's important here that we must have the fluorine in excess, as in we have no more than half an equivalent of the bromine. Otherwise, we'll just get the dibromide product. If we keep the bromine in lower concentration, we should just get monobromination statistically, and then the bromine will run out. This is quite a common trick in making these types of molecules. Now, we actually form this regiochemistry just for the standard reasons of stabilizing a carbocation. The best place to leave the carbocation will be just here, labeled in green, because if I react here, my intermediate carbocation is stabilized by delocalization, and it can use the other side of the molecule to extend its pi system further. That extra delocalization is not possible if the carbocation formed in this position, for example. So with the position also being less hindered than these ones in orange, we get selectivity for the substitution pattern that I've drawn above. Now we've got that bromine in, that was for the Sonogashira reactions, but going forward we needed another halogen. We can just use the old school method for iodination using the strong oxidizing agent in nitric acid. Now, the major site of reactivity has been blocked on the left-hand side of this starting material, but there's still one on the other side. For the same reasons of stabilizing the carbocation, we'll get the iodine selectively in this final remaining reactive position. So my next step will be to do some Sonogashira couplings. I've got the more reactive carbon iodide bond to deal with first. So I'm just going to use a palladium 0 source. Use whatever your favorite is. Let's just use the Tetrakis triphenylphosphine palladium source here. We need to make sure there's a copper salt in there and triethylamine to make the organometallic and an alkyne. So I'm just going to use TMS acetylene. This is the smaller protected alkyne, but importantly, just make sure I've got one equivalent of this. So we'll end up with this alkyne substituted on the right-hand side. And all we need to do next is do the same with the other substituted alkyne. So that's TIPS acetylene with the isopropyl groups. Again, we only need one equivalent of it, although we could put it in excess this time. Same conditions, the Tetrakis palladium complex, copper iodide and triethylamine. And this is where I would store my material while I made my other heterocycles. So we discussed the syntheses of those quite extensively on the other slides, so I won't repeat myself here. Doing some protecting group dancing will help us go forwards. So we've got our common intermediate here, from which we could make libraries of compounds to test for their electrical properties, very much in a similar way to how medicinal chemistry could work. But for our specific molecule, we're going to need to take the trimethylsilyl group off first. So that's the sterically less hindered one that I'm just highlighting in green. So we can just use some milder conditions. In fact, common ways of doing this would just be to use potassium carbonate in methanol. This is just a slow release of methoxide because the potassium carbonate is only partially soluble. The O- can form a strong bond to the silicon center and release the alkyne. Now the alkyne is free, it'll be able to do the click chemistry. So the specifics of the reaction conditions, you'd have to vary them a little bit. There are lots of different variations that you could use, but they're all based on copper 1. So on my right-hand side, I'm just going to introduce my electron-rich heterocycle by using this azide, and this is doing our click reaction, our copper-assisted cycloaddition. And then for the final couple of steps, we need to use some more aggressive deprotection conditions to get rid of the triisopropyl silyl group. A much stronger set of conditions, what would work here would just be to use TBAF. So that would just deprotect the alkyne. TBAF is an F- source. So silicon fluorine is pretty much the only bond that's stronger than silicon oxygen. So this is an even stronger nucleophile for the silicon than the methoxide was. And once we've got the free alkyne, we can just do another click reaction, the copper 1 catalyst, and our electron deficient heterocycle component. And this will take us to our product. So hopefully with those colors, you can see how we could introduce different heterocycles. We could clip on completely different things where the purple and orange bits are. We could change the electronics there and affect the energy levels of the whole molecule and fine tune some electrical properties. We could also add on other substituents to help with crystal growth when we're trying to make this into a semiconducting device, such as a diode. And we can just make the smaller heterocycles separately and bolt them all together pretty cleanly at the end with minimal byproducts. This will mean we won't have to do too much purification near the end, which is good because chemical byproducts can really screw up device manufacture when you're making solar cells or OLEDs, for example. If you enjoyed the discussion, please do give it a like and do feel free to drop me any comments in the box below.